Hello student, today we are going to learn Davisson and Germer's experiment. In Davisson and Germer's experiment, the dual nature of matter was physically explained by the scientists Davisson and Germer's with their experiment. This is the figure for the Davisson and Germer's experiment. This experiment is a simple experiment in which electrons are generated by means of a heating filament, which is accelerated by means of applied potential, and that accelerated electron is allowed to fall on a nickel crystal, and that diffracted electron are detected by means of a electron detector. Now this is a simple method. Now let us see the diagram. Here is the heating filament. The electrons are generated here. Now here are the two plates which are acting as a anode. A potential is applied in between these two plates. Due to that potential, the electron get applied a force, electric force, and due to that electric force, the electron get accelerated. That accelerated electron emerge with a certain velocity and certain kinetic energy. Now that accelerated electron strikes on the nickel sulfate and get scattered with an angle. That angle is measured by means of electron detector. Now this experiment consists of two parts. The first part is to accelerate the electron, and second part to measure the angle of scattering. Now let us see the theoretical part of this experiment. Now if a potential of phi electrostatic unit is applied in between these two plates, due to that a electric field or electric force which act on that electron, which is having a charge E, is a P into E. Phi is a potential difference, E is the charge of the electron. This much electric field or force will act on that electron, and due to this the electron get accelerated with a velocity phi, and due to that velocity phi, the electron will have a kinetic energy half mv square. Now this kinetic energy will get to that electron due to that force, and therefore it is said that the kinetic energy acquired by the electron due to electric field shall be equal to the electric force. Now thus we can equalize the kinetic energy with that of the electric force V into E. Rearrange this equation. If we rearrange this equation, transfer 2 on this side and m on this side, we will get V square is equal to 2 V into E upon m. Take the square root of this, we will get V is equal to square root of 2 V E upon m. Multiply both sides by m. If we multiply here by m, it will be V into m. If you multiply here with m and then transfer that m inside the square bracket, inside the square root, it will give m square. Now this m square and this m, one m will get cancelled, and we will get the final equation m v is equal to under root 2 m v into E, equation number 1. But according to the de Broglie's equation, lambda is equal to h upon mv, or rearrange it, mv is equal to h upon lambda, equation number 2. Now from equation 1 and 2, put the value of mv in equation 1, we will get h lambda is equal to under root 2 m v into E. Now rearrange this equation. lambda is equal to h upon under root 2 m v into E, or square root of h square upon 2 m v into E. Now here substitute the value of h, value of m and value of E, and convert the potential V, electrostatic unit, into volt. After calculation, we will get the equation lambda is equal to square root of 150 upon V volt into 10 to the power minus 8 centimeter. Now 10 to the power minus 8 centimeter is equal to angstrom. Therefore, the lambda is equal to square root of 150 divided by V volt angstrom. Equation number 3. Now this equation 3 is important. This says that the wavelength of accelerated electron is depends upon only one factor, that is potential applied between the two plates, and therefore if we apply 150 volts, then wavelength of that electron will be 1 angstrom. If we apply a potential of 15,000, then the wavelength of accelerated electron will be 0.1 angstrom. That means we can generate a electron with a known wavelength. Therefore, the wavelength of this accelerated electron is known, which depends upon this potential. That is due to this equation number 3. Then the next part of this experiment, that accelerated electron is allowed to strike the nickel crystal, and when it strike the nickel crystal, it get diffracted. Now electrons of definite wavelength get diffracted along definite direction. Now here is the mobile electron detector, and here is the circular scale. With the help of this electron detector on the circular scale, if you move it, we will get the angle of scattering, angle of diffraction, or angle of scattering. It is also called as a glancing angle, where we get maximum intensity and measure that angle, it is theta, by means of this circular scale. Now this is the first order measurement, and therefore for first order measurement we will get an angle theta. By substituting the value of theta and d is the interatomic distance or interplanar distance for the nickel, it is 2.15. in the Bragg's equation, that is n lambda is equal to 2d sine of theta. Now n is 1 because we measured that angle for first order. D is 2.15 and this angle is theta, which we measured. Now thus we can get the wavelength lambda from this second part. This wavelength is found to be agree with the wavelength as we obtain from equation 3. That means in the part first we will get that wavelength which depends upon the potential difference of these two plates. This wavelength and the wavelength calculated by means of using this theta is the same. This indicates that the electron is having a wave character or the wave nature. Now the practical nature, particle nature of the electron is already explained by means of the experiment with that of discharge tube, in which the paddle wheel is moved by means of the electrons. Therefore, electrons are having a particle nature as well as wave nature, or particle character or the wave character. In this way, the dual nature of electron can be explained physically by means of Davisson and Germer's experiment. Thank you.